Dear students, here we will discuss first going to the wave pack. Before going to the wave packet, first I will write a Schrödinger wave equation. So the Schrödinger wave equation can be for a particle of mass m of particle of mass m which is subjected to some force which is subjected to some force like potential, and this potential is the function of R and T. The Schrödinger equation for this particle will take the form, and we can write it like this one: iota h cut partial over partial t into psi of R t is function of R and t. It will be equals to minus h cut square over 2m into del psi of R t plus v of R t into psi of R t. Here we know that general form of Schrödinger wave equation is H psi is equals to E psi. So here H is the Hamiltonian operator. H is the Hamiltonian operator. Correspondingly, it gives us the total energy of the system. So it's equals to where iota h cut partial psi over partial t is equals to minus h cut square over 2m del psi of rt plus v of rt psi of t. So here this del is the Laplacian operator. So it has a different values in different coordinates, like in spherical, polar or cylindrical coordinate or Cartesian coordinate. It has its own its values are always its value is equals to partial square over partial x square plus partial square over partial y square plus partial over partial z square. This is the Laplacian operator, and the value of psi then uh, and varies in the different coordinate system, so we can use the Laplacian operator accordingly for the different coordinate system. So here now we comes to the free particle. So free particle, what is now first we need to know that what is the free particle. Free particles are those particles for which V of RT is equals to 0, that is not that are free from the influence of any force. There is no force acting on the particle of mass m, free from force, any kind of force. So the Schrödinger wave equation for the free particle, we can write it like this one: Schrödinger wave equation for free particle. It will be equals to iota h cut partial over partial t psi of R t. It will be equals to minus h cut square over 2m into del psi of RT. So by putting V of RT is equal to 0 for the free particle. So this is our equation, Schrödinger wave equation for free particle. So what is the psi? Here the psi wave function associated with the free particle psi of RT is equals to a e power iota k dot r minus omega t. So the solution of this Schrödinger wave equation, which is equals to the wave function psi, takes this form. So here the a is the constant, a is constant, and so this solution subjected to some condition. So condition that omega and k should satisfy the equation omega is equals to h cut k square over 2m. So they are subjected to this equation. Let's suppose this is one is the equation 1, and this condition for this solution. So psi will be the solution of Schrödinger wave equation for free particle only when omega and k satisfy this condition, which can be represented by A. But according to the de Broglie hypothesis, the condition A, which I have written, that now I can write it again, that omega is h cut square over 2m, that is the Schrödinger wave equation, that is psi for the free particle, psi is equals to e power iota k dot r minus omega t. It will be a solution of the free particle only when it satisfies this equation. But according to the de Broglie hypothesis, de Broglie says that the energy and momentum of free particle should satisfy this equation. Alternatively, it's equals to h cut square over 2m. So we can write it equals to B. So again here the equation 1, that is psi is equals to a e power iota k dot r is equals to omega t. But here you know that in quantum mechanics we always talk in terms of probability density, because psi itself is nothing. We have already discussed about it. Here the probability is equals to a e power iota k dot r minus omega t into its conjugate a into e power minus iota k dot r minus omega t. So the probability will be equals to a amplitude square. So this can be an equation number 2. So for this equation tells us, so the plane wave, this tells us that this is the plane wave. It represents the plane wave psi, which is associated with the material free particle, and this plane wave will be the solution of Schrödinger wave equation for the free particle, and its probability, when we calculate the probability, this wave function is equals to amplitude a square. So what it represents, so the plane wave of this type represents a particle whose probability presence is uniform throughout all the space. That's a problem, that how we can find the particle all over the space. As this equation, what this equation tells us, that the probability of presence all over the space. So this is the difficulty with the free particle. That is how we can find it all over the space, has spread its probability spreading all over the space. But here we know that uh, there is the advantage of the quantum theory is that the quantum theory obey the superposition. So according to the superposition principle. So superposition principle tells us that every linear combination of the plane wave which satisfying the condition is also the solution of Schrödinger wave equation for the free particle. That is, you know that in superposition, if we said that if psi 1 is the solution, if psi 2 is the solution, then their combination psi 1 plus psi 2 will also be the solution. This is the word which principle of the superpositions tells us. And so this solution should also satisfy the condition, and that condition is omega is equals to h squared k square over 2m. Then this superposed solution will also be the solution of Schrödinger wave equation for the free particle. So here we can take an advantage of superposition principle, and we says that takes a linear combination of different plane wave instead of one wave. So the linear combination will be equals to 1 over 2 pi 3 by 2 under root g of k. Okay, sorry, the equation is like this one. So here I can write it. This is the integral. Actually, the integral of g of k e power iota k dot r minus omega, which is the function of k into d cube k. Here the d cube k is infinitesimal volume element, which is in the k space dkx, dky, and dkz. And here what is the g of k? G of k, which can be a complex and it representing the group of the wave, and it must be sufficiently regular to allow the differentiation inside the integral. That is, any square integrable function can be written in this form. As we know that for the psi to represent the state of the system or to represent the particle, it must be the square integrable. So this equation will also be the square integrable. So this equation, so any wave function which is the superposition of the plane wave is called a three-dimensional wave packet. So what is this equation is representing? This equation is representing a three-dimensional wave packet. So here we take an advantage of wave packet, as we have already seen that the individual wave, that is the amplitude square was equals to a square, that its probability was spread all over the space. So we have taken the advantage of superposition principle, and according to the superposition principle we can take the wave packet associated with the free particle, and this wave packet can be represented by this equation. So this equation will also satisfy this solution, this condition. So when it satisfies the condition, this three-dimensional wave packet, if it satisfies this equation, this will also be the solution of Schrödinger wave equation. Now what is the advantage of taking this three-dimensional wave packet? So we have already interpreted this uh, one, that here the wave packet, we know that the individual wave within this wave packet will interfere constructively, and their amplitude is adjusted so that they interfere constructively within the certain region of the space and destructively outside this region. So here within this region there will be the maximum probability of finding the particle. So here we can localize the free particle when we associate a wave packet with it instead of the single wave. So the free particle become well localized. So we can make it localized, we can define it, but a wave function associated with it cannot make it localized because its probability is spread over all the space. So here this is the advantage of using a wave packet uh, as a solution of Schrödinger wave equation for the free particle. So in our coming video we will discuss in detail about the wave packet. So thanks for watching. For more videos please subscribe our channel.